These are the notes on calorimetry, and these notes will help prepare you for the energy in food lab that you're going to do tomorrow. So what is calorimetry? We've got a picture of a calorimeter right here. A calorimeter measures the amount of heat transferred during a reaction. A calorimeter is a device that stops the transfer of heat between the inside of the calorimeter and the surroundings, which makes it a closed system. So that inside is this small can right here with the water. And then this outer large can is to kind of keep that whatever's happening inside closed or stable, so there's nothing else going on. The calorimeters you're going to see in the videos you watch for the lab aren't going to have this outside can, so that's something to consider when you are thinking of what are sources of error. How would that impact our lab that we do? If you are aware of the lab that we did in person, that lab had a styrofoam cup because our reaction took place inside. But what we're going to do today, or for our class, is that we are going to have that reaction happening outside. So the ones you see in the videos will look a little different than maybe your friends saw if they were in in-person chemistry. So calorimetry is a technique of using a calorimeter and measuring the quantity of heat exchanged. And with that, the energy from a chemical reaction is absorbed in the container of water. So the change in temperature of the water provides a measure of the amount of heat released or absorbed in the reaction. And so why this works is because we can measure changes in temperature of the water to determine, did water get energy from a reaction, or was energy taken from the water in a reaction, so we can calculate what was happening in a reaction like burning or even dissolving something in that water. And again, that reaction can happen in two places. It could happen in that calorimeter water, which is not the type of lab we're going to do, or outside the can to heat or cool the water through the can. And so we've got that. It's normally an aluminum can that reaction is going to happen outside. And considering why would a metal can be used inside a calorimeter instead of something like plastic, we want to consider that the specific heat of metal is fairly low, so that heat will transfer from whatever reaction, like a burning combustion reaction, it'll easily transfer through the metal to the water, and so that energy is going to the water and not getting absorbed by the can. So that's why you'll see metal cans used in each of those experiments. If you want the energy to stay contained, you would use something like styrofoam if we were doing a reaction where the reaction was inside. Instead of using a can, we would actually use something like a styrofoam cup or something that will keep that energy in. All right, and we are in the lab that you were going to do. We're going to talk specifically about food energy. And in science classes, we measure energy in units of joules or kilojoules. When discussing chemical energy we get from food in our daily lives, the unit of energy that we're most familiar with is calories with a capital C. And so you can see on this nutrition label that I just posted on there, and this is for potato chips, which we're going to do an example on later. That you'll see that here this calories is capital C calories. And when we're talking about our energy units for food, we have capital C calories and we also have lowercase c calories. So it can get a little confusing. So some helpful conversions we're going to use, since we're going to be most familiar with joules from our calculations that we've done in the past. Especially with our specific heat formula, our Q equals MC delta T. Conversions to know are that 1 calorie, lowercase c, is 4.184 joules. So we're going to use that in our example problem, and you're going to use that relationship in your lab. And that lowercase c, though, is not actually what we measure our food energy in. We actually use the capital C calorie, and 1,000 lowercase c calories is 1 uppercase c calorie. And so a dietary big C calorie is what we measure our food energy in. And that's what you would see on food labels. One big uppercase calorie is sometimes called a kcal because it's a kilocalorie, 1,000 calories with that. So if you've heard any of those terms before, we are going to see those in our calculations. All right, calculating heat energy Q, we are going to use this Q formula that you saw in specific heat notes, where that, again, C is specific heat of whatever substance is changing temperature and that we have a mass of, that we're then finding the energy, the heat energy of. And so again, for a pure substance with mass of M, the expression of heat energy can be written as that Q equals MC delta T. Where Q is the magnitude of heat or thermal energy measured in joules. M is mass. C is specific heat of that substance, and that is a constant for the substance, and that's measured in joules per gram times degrees Celsius. And then we also have change in temperature in degrees Celsius, where change in temperature is final temperature minus initial, like that. And one thing we want to make sure, because we're going to be dealing with multiple substances in the lab and in our examples, is that we want to make sure if we're using, let's go back up to this picture, if I'm looking at calculating the energy of water, I want to make sure I'm using the mass of the water, the change in temperature of the water, the specific heat of the water. But if I'm looking at, well, these look like peanuts to me. If I was finding, well, what is the energy of my peanuts, I would have to use the mass of the peanuts, the specific heat of the peanuts, the change in temperature of the peanuts. And that's not something we can easily find for the peanuts, which is why we use the water. And so to calculate Q, all these values need to be for that same substance. And we're going to use these with water for a calorimetry calculation. And so your measured Q with the calorimeter is going to be the heat that is absorbed by water. Because we're going to be doing burning of food, that water is always going to be heating up. And so we're going to use the specific heat capacity of water, so that 4.184 value. And water is kind of our surrounding, and so when we're looking at what kind of reaction is happening to change the temperature of the water, if the temperature of the water increases, the reaction that heated it was exothermic and released energy. And those are all of the reactions that you are going to see in our calculations today and that you're going to see in the videos are going to be exothermic because this specific calorimeter lab is dealing with burning, which is exothermic. It is possible to have that temperature of the water go down due to a reaction in the calorimeter. And if that water decreases in temperature, that means that the reaction cooled the water, making it an endothermic reaction, meaning that the reaction cooled energy by taking it from the water. Absorbed energy by taking it from the water. So with some background, I've got two examples. I'm going to go through one example with the work, and then I'm going to just have you show you the answers for the next example if you want a second one. This is similar to what you're going to see on your lab. And so if you're struggling with lab calculations, you can always reference this. All right. So for our example, calculating energy of a food item using a calorimeter. So a calorimeter is used to determine the energy in a potato chip. 100 milliliters of water is poured into the calorimeter. Use the data provided to calculate the following. And so with this, and if this is hard for you to picture, you can go to one of the videos for our lab that is posted for tomorrow if you want to watch this reaction. But what's happening here is this is referencing that a potato chip is going to be burned below here. We have 100 milliliters of water in here. And then with a thermometer in that water, that's how we're going to be able to measure the temperature. And so we're given that information below. And then I'm given a data table over here. So first thing I'm asked for is the heat that is absorbed by the water, which is going to be the same as the heat released by the food. So that I'm going to use my Q equation for, and I'm going to, because I don't know the temperature change, of my food, I'm going to be looking at using this for my water in the calorimeter. So I'm going to be looking for what is the Q of my water. So in order to do that, I'm going to need to use the mass of my water times the specific heat of water times the change in temperature for my water. So looking at the different things that I have here, I am told that I have 100 milliliters of water. Well, the density of water is that 1 milliliter is equal to 1 gram. So the mass of my water, if I have 100 milliliters, that's going to equal 100 grams of water. And so I know that, and you're going to see that value on your lab tomorrow as well. So we have our mass of our water is 100 grams. C, the specific heat of water. The specific heat of water, we saw that in our specific heat notes, is that value C, 4.184. And then I need, what is the change in temperature of my water? Looking at my data table over here, I have information about the initial mass of my chip and the final mass of my chip, because remember, we are burning a potato chip. And then initial temperature of the water and final temperature of the water. So to find the change in temperature for my water, I'm going to do final temperature minus initial. So 27 minus 23, final minus initial. So that was 4 degrees Celsius. And that, since that's a positive number, that means my water had an increase of 4 degrees Celsius for that temperature. So plus 4, and then I'm going to multiply those values together to figure out how much energy the water gained. So 100 times 4.184 times 4, that is 1673.6. So 1,673.6 joules. That is the heat absorbed by my water in joules, but then that is also the heat released by my food. So water gained this much heat, which means that my food released this much heat. All right, our next step is now that we're going to kind of change this into those food energy measurements. So next we're going to take that heat absorbed by the water calories, which is the heat released by our food. So the heat released by our food was this here. We're going to go from joules to calories. And so in order to do that, I'm going to have 1673.6 joules. Whenever I have a conversion factor, I like to set it up as that conversion factor. And so I want to get rid of joules. So joules are going to go on the bottom, lowercase calories on the top, and 1 calorie is 4.184 joules. So I'm going to take my 1,673.6 divided by 4.184, which gives me 400. And the joules units cancel, so this is lowercase calories for that heat released by the food. Next, that heat absorbed by water, capital C calories, is the heat released by my food in capital calories. So I'm going to go from lowercase calories to the uppercase calories, which is what we measure food energy in. So 400 lowercase calories from my previous problem. Well, lowercase c on the bottom, uppercase C calories on the top, because that's what I want. So 1 calorie is 1,000 of those little calories. And then again, that is a division. So I'm going to move my decimal 3. So 0.4 capital C calories is my heat released by my food. And again, I can see my units of calories canceling so that I can check that I set that conversion factor up correctly. All right, 2 more steps. Now taking this calorie, we want to look at, well, how many calories per gram, just like our different elements have different masses. Different foods are going to have those different masses. So we want to look at calories per gram. That kind of tells us how much nutritional content is in our food. So we're going to calculate from our data that's over here, what is that measured energy content or heat per gram of food. So we're going to take our capital C calories and divide by how much of that food burned in our experiment. So that's 0.4 capital C calories divided by grams of food burned. Well, we didn't even calculate that yet over here. I've got the initial mass of my chip before it was burned, my final mass of my chip. I think I flipped these. Hold on. Oh, let's change this. This might be a 31.95. We're going to change that there. And I'll change that on your notes. So then I do what is my final minus initial, because that should go down in mass when it gets burned. So we've got 31.95 minus 32.28. So 31.95. So the mass of the chip consumed, so this went down by negative 0.33 grams. And with this, we're going to just use we're going to drop the negative on that. So that's 0.33 grams. And I can then divide my calories by my grams. So 0.4 divided by 0.33. So I've got 1.2, and that is calories per gram. All right. So from my change up here, and I might update that on your notes. It might be a little different. I don't know that I'm going to re-record this video, but if you see a different number up there, you'll know why, or maybe I'll say this is what the actual final mass was, because I think I did a typo. Now finding that percent yield, compared to what is that accepted energy content in the chip. Percent yield is going to be our measured energy content divided by our accepted energy content times 100. And so with that, we're going to go, what is our measured? That's from our experiment, 1.2 divided by accepted, which for the chips is 5.71, times 100, 1.2. And so this gave me a percent yield of 21.0%. And that percent yield is really low. We don't know how this data over here was collected. So maybe it was errors in that calorimeter. Maybe it was errors in how that chip was burned. So that's something that we're going to consider when you watch the videos, and then looking at your data is that percent yield. How close are we getting to that accepted value, and what errors may have happened along the way? So there's that example there. Again, I apologize about that number at the top, and that might be a little different or a little off. I went through the second example and showed my work here. Feel free to take a look at this and go ahead and see what, or pause the video, take a screenshot, give this one a try if you need to, or if you want to for practice. All right. And lastly, there is an optional video linked. What is a calorie? The description is there for you. So just a little bit more information on food energy and how we get them and how we use them.